Now we are.
Yes. Okay. So, on Wednesday, we had just started, I'm actually going to flip back the page, talking about our second biomolecule. So we finished talking about carbohydrates, aka sugars, looking at how they are made. So we spent a lot of time talking about hydrolysis and dehydration synthesis, and we're going to keep talking about those because that's how we're going to take apart and put together all of our biomolecules. And we really looked at what are carbohydrates good for, right? And how would we recognize them? So we really talked about things like hydroxyl groups, polarity, right, and carbonyl groups. And at the beginning or end of class, we had just started to talk about the beginning of lipids, right, the introduction of them, okay? So we talked a little bit or introduced some possible functions of them. We're going to spend some more time talking about this and talk about some very specific examples of the use of lipids. Okay? But we spent most of the time looking at how would we recognize a lipid if we saw it. Okay? So we talked a lot about the lack of oxygen, right? So the presence basically of these long hydrocarbon chains. Okay, so literally hydrogens and carbons in long chunks. Okay, so the desert without oxygen. Okay, so we said that this makes it nonpolar, okay, or does not play well with others. Okay, so remember when we thought about this, we said, well, with carbohydrates or with sugar, you could take sugar, right, and pour that in water, and what happened? It dissolves, right? So we can say, well, when we're thinking about polarity, when we think about having a lot of oxygen, about having a lot of those hydroxyl groups, right, that makes it play well with others, makes it dissolve in water. When we're thinking about lipids, things like fats and oils, right? If I take those and I pour them in water, that makes them what? What happens when I pour olive oil into water? It doesn't mix, right? It just kind of sits on top, it floats, right? Separates out. Okay, so this is a good example of how nonpolar things, right, or things that have these long hydrocarbon sections don't usually play well with other things, right? They're non-polar. The other thing we talked about, let me get another color here, was the carboxyl group. And we compared this and created this little box up here to the things that were present in the carbohydrates, specifically the carbonyl group. Okay, because remember, a lot of these things are named very similarly. They look very similar, and this is something we want to make sure that we're very cognizant about. This is one of the reasons we're making that study guide as we go, just in case, right? And we're going to draw these little boxes a lot as we go, so we can do these comparisons and we can reinforce this potential issue and try to cut this off at the pass. So our carbohydrates have the carbonyl group, okay? The carbonyl referring to, having the carbon double bonded oxygen, okay, but the eel just referring to having this kind of boring hydrogen sticking off the side, right? But the carboxyl group, which is what we have in our lipids, we still have that C double bonded oxygen, but instead we have the oxyl on there, right? So that's referring to our hydroxyl group that's sticking off the edge. Okay, and we're getting nice and familiar with hydroxyl groups, right? We had a lot of them in our carbohydrates because that's what we were using to do our hydrolysis and dehydration synthesis. So the names will tell us a little bit what we need to be looking for, but practice is going to be the only thing that's really going to help us associate it with the appropriate biomolecule. Okay, this is where we left off on class on Wednesday. Were there any questions on this before we moved on? All right, so let's take a look at some delicious lipids. All right, so just like we did with carbohydrates, let's look at how we make or break lipids. So one of your standard lipids, your food-based lipids, is a triglyceride. This is the kind of lipid you find in butter or fats. Yum. All right, and so here we see, despite the fact it looks a little overwhelming because it's bigger, okay, this is the same boring old process that we've seen before. So let's ignore my blue boxes for right now and just focus on the drawing for a second. We're going to come back to my blue boxes. All right, so if I look at my lightest tan box, okay, I see some familiar business. Stop. Okay, so we could even, listen, there we go. Call this Janet, right? And my kind of medium colored taupe, whatever, boxes we can call Carl. I guess there's 3 Carls in this story. Okay, but the key here as we look at these, despite the fact that we have several unfamiliar things, is that there are pieces in here that are already familiar. Okay? In particular, okay, our goal here is to make one large molecule. And when we're doing that, right, we have a single Janet, right, and single Carls. So they each have individual hands with individual mittens. Okay. Now we know what these are called now. Right? On Janet, I know that this is a hydroxyl group. Okay, and on Carl, what is that? Carboxyl. Good. Try to clean this up a little. Okay. Key here, though, is I have 2 hands and 2 mittens to work with. So I'm able to go through the same process as before. Now let's go ahead and address my first box. If I'm going to take single Janet and single Carl and combine them together to make a couple, Janarl, right? They're holding hands here. So I'm going to take two smaller molecules and combine them to make one bigger molecule. Am I doing hydrolysis or dehydration synthesis? With confidence? Dehydration synthesis. Excellent. Right, I'm creating, right, a big molecule, okay, like something in butter. Or, right, I started with 1, 2, and this is 1, 2 words long. Okay, however this helps. Okay, let's real quick look at how this would work so we can feel the familiarity. Okay, even though, good gracious, I'm so sorry. Even though it looks different. All right, so let's just look at the top connection. All three of these are going to work the same way, right? So here is, just erase this so I have a little bit cleaner of a start. Here's Janet and Carl's hands. Okay, remember if I'm dehydrating, my goal is to get a water out. Hey, remember a water is, am I drawing? Okay. H2O. All right. So, I know I need my two hydrogens. Those are my mittens. First thing I'm going to do is go pull off some mittens. So let's take a mitten from Janet and a mitten from Carl. Check, check. Easy peasy lemon squeezy. Now I need an oxygen. So I need to take somebody's hand. Okay, it does not matter who. Okay, I just like to pick on Carl. So I've designated the taupe box to be Carl. So I'm going to take Carl's hand. Sorry, Carl. All right, taking that. So there's my water. Yum. All right, so we've dehydrated. Check. All right, so now all that I have left then is one hand. In other words, one oxygen, and that's still on Janet. And that's the hand that Janet and Carl are going to hold hands on. So we're going to create a bond between Carl and Janet's hand, or the oxygen. Okay, and that process we did on the top one is the exact same process we would do on all three. Okay, so even though this looks very different, right? Pulling mittens and pulling hands so we can make water is the same process that we did when we did this with our carbohydrates. Right? It just looks really intimidating because this is such a big molecule to be doing this with. And now we've got carboxyls sitting there. Okay. Does everybody see what I did with Janet and Carl up here? Okay, my goal is to do this so many times it feels boring. Okay, so let's look at my bottom blue box now. So remember when we did this with carbohydrates, okay, we called that a covalent bond, right? So let's again bring up a little box, do a compare. And remember that was just a plain carbon to an oxygen to a plain carbon. Okay, this here, what we've created, I need a new color. I'm going to circle it somewhere else. This bond. The same bond we did with Janet and Carl too. I just want to circle over the one we'd already drawn a lot on. Okay, this bond is called an ester bond. I don't name these things, right? I'm gonna shoot the messenger. Right? Fundamentally, right, we did the same process. That's what bullet 2 is saying, right? To do this, we didn't do anything special. This is like a whole chemistry thing. Okay? The reason it's named something different is because instead of using that boring old carbonyl and the hydroxyls to do this, right? Because remember, we used just OHs to make this bond. Okay, to make an ester bond, okay, we had to use Carl's carboxyl. I still had a hydroxyl on it, right? But we still have the remnants of that carboxyl hanging out. And we don't care too much, okay, but this does change the relationship of the bond a little bit. Does everybody see that very specific defined detail difference? Okay, so our carbohydrate version of everything is sort of the very basic low-key version. Right? It was a much simpler, smaller molecule. Right? We're using simpler pieces, just our plain hydroxyls to do things. So now that we're getting into lipids, we've got bigger molecules. Okay? They're somewhat more complicated. So even though we're going to use all of the same processes that we learned, okay, we still have bigger, more complicated outcomes. So it's an ester bond. And we'll see for each of these biomolecules, because we have different compounds, right, in this case, that carboxyl group, it's going to change the nature of what we've created. Okay. Any questions about what we've done here? I have very bad handwriting. This feel okay? Okay. So we've added a new tryst, but like always, we're trying to keep that similarity or that familiarity there for us. Okay. So, as I mentioned, there is several different things that we can use lipids for. So this is one of the additional, that's in the way, there we go. Additional things or features that lipids get used for. So this is where we really already talked about food. I'm team butter and oil, don't get me wrong. But we can do some things with lipids that make them almost more useful than delicious, delicious food. So what we have up here is a phospholipid. So if I take about here. Okay, everything below that kind of purpley line is the exact same thing that we saw on the previous page. Okay, just instead of 3 tails, right, or 3 of those boxes, we only have 2. Okay, so remember when we're looking at these things, okay, this is one of those chemistry lazy hand things. Every time we have a kink, what do we have? Carbon. Good. Right, so these down here are our hydrocarbon chains. Just a really lazy way of showing it. Okay, so there's our ester bond. Oops. Yeah. Right. Here's your double C to O to C. Right, so that's what we did with Janet and Carl. Make that small. Just like we had it here. Ooh, I can't do both. You're rude. Right, C to O to double O. Okay, so we've basically just taken this whole thing and twisted it vertically. Right, and then killed one of the tails. Bye-bye, blue box. So the bottom half of our image is going to act like we're used to seeing it act. So let's just focus on the bottom half of the image for this second. So if we have long hydrocarbon chains, okay, that's the desert without oxygen, right? Clean this up or this is going to be way too much drawing. I'm going to put that back on here, don't worry. Just going to put it over here. So here's our long hydrocarbon chains. Okay, so we're familiar with this already, right? The desert without oxygen. So we already said these have no oxygen, and having no oxygen means that we're nonpolar. Okay, these are all things that were definitions from our very first page, right? So we're just going to carry all of that stuff over here to look at it. So all of those things together come around to this definition here. Hydrophobic. Okay, now this is something you guys have already told me. Okay, we're just putting some words to it. Okay, so phobic, meaning fearing, right, to fear, and hydro meaning water. So this just literally means water fearing. All right, so you guys told me this already, right? If you take a lipid, an oil or a fat, and I dump it in water, right, it goes chicken. Okay, it doesn't want to play with it, pulls itself out, it doesn't mix. Okay, so that's all this is telling me. We knew this part already. Okay, but this isn't just your standard triglyceride, right? This has something different on it. So instead of having 3 of those hydrophobic tails, let's change colors. We've done something different for our third piece. Okay. We've added a whole different kind of tail. Okay, we added this phosphate group. Okay. What's new or interesting about this phosphate group? So the phosphorus is on there. What else? The oxygen. All right, so now we have our phosphate, its namesake, and it's surrounded by oxygen. So now this whole segment is loaded, right? 1, 2, 3, 4, 5, 6, 7, 8 oxygen. This one tiny little area. I'm just going to put my notes over here because I'm out of space. So now we have many oxygen. Well, what's that going to do? Make it love water, right? Remember from our carbohydrate story, many oxygen makes it polar. Polar plays well with others. So that's what this statement over here says. Okay, so that first part still says water. Philic or phile literally means loving. Right, so now we have this really strange lipid that has this dual nature business. Okay, so the bottom half of it fears water, and the top half of it loves or will mix with water. Okay, so this gives it the opportunity to do some really interesting and amazing things. Okay, so before we flip forward and see what it does, does everybody see the structure? And understand how we've gotten to this point? Make sure I'm not ripping notes away from anybody. Okay, so here's why what we've created is so important. So here again, I've sort of done like a lazier drawing of it. But we have the same concept, right? Here's our hydrocarbon tail. Right, and the I don't think I spelled that right. Does not matter. I don't know where to stick this thing. All right, so this is why this setup matters. So remember that our hydrocarbon tails are nonpolar. Okay, so they don't play well with others. So I like to think of these as being scaredy cats, right? So they're literally going to tuck tail. That looks like a D. Tuck tail. Think like tuck tail and run. So our nonpolar tails don't want to be around water. Like they're afraid of it. So the best way to prevent being around water is to, as we see here, tuck the tails in, right? So they're going to get together and tuck their tails together. So that way the only thing they're interacting with is each other. That's neat. All right, so they kind of create their own little closet, their own little space in which nothing dangerous can enter. Okay, these polar heads then, as we see, stick out. Okay, kind of creating a barrier, but that's fine, right? Because those polar heads like to play with anybody. So they can stick out because they'll interact with anybody that shows up. That's fine. So this is what we end up creating. Let's clean this up a little bit here. We end up creating basically a wall, okay, literally a membrane or a barrier. So this middle area, let's pick a color that'll actually show up, maybe, ends up becoming the barrier itself. So here is our wall or ring or protection. Literally just says barrier. Let's put it up here. Okay. Nothing really can get through there easily because they don't want to play with you. They're afraid. Very, very afraid. Okay. On either side of this, though, right, those polar heads, they'll play with you. So on one side, right, these happy, snappy heads will be exposed to the open liquids, right? So here we have the outside world. Okay, which is wet and nasty and mean and cruel. But the polar heads don't mind because they play well with others. Okay, on this side, on what is the right-hand side of my drawing, I'm going to pull this over because I think if I write over there, you guys will be able to see. Okay, that's going to be the inside of the cell. Okay. Now remember, the inside of the cell is also wet because it has things like cytoplasm. We'll talk about this more when we get to the tour of the cell. Okay, but the inside of the cell is full of gushy, squishy parts. But polar heads don't mind. So stuff outside of the cell can't get across very easy because there's this barrier of don't touch me. Okay? And stuff inside of the cell can't get out easily because there's the barrier of don't touch me. Okay, so we end up with this really good barrier of protection that holds the cells together and keeps nasty, dangerous things from getting in. Thanks to the wall of, I said don't touch me. Okay, so we'll end up visiting this again because all cells have this membrane. So it becomes a really important design, okay, and an important feature to have the layer of don't touch me and yeah, this is fine. I feel good. Not enough mind-blowing with how amazing phospholipids are, but okay, all right. Okay, the last thing, not the last thing, the last thing we're going to care about that lipids do are function as steroids. Now, this is also probably a term that you've heard before. So here, if we look down at my pictures, we see that I've altered the version or the view that I've used for my lipids. So everything that we've done with lipids up to this point have been largely chain versions, right? So we've had very long chains or deserts of our hydrocarbons. Now what I want to do is change my chains into rings of hydrocarbons. Okay, so it becomes more important than ever to really remind ourselves, okay, that every time that we see a kink or a bend, that each of these kinks, right, is a carbon. Yep, yep. Okay, so let's start with, if I was presented with one of these rings, how would I be sure that I'm looking at a lipid and not a carb, right? Because we saw carb rings as well. So let's take one of these that has quite a few. So let's take cortisol as my example. That has kind of a few hydroxyls on it, right? So if I were given cortisol on a test and I was asked, what type of biomolecule is this? Now we've only got the two to pick from right now, right? So we know it's got to be one of those two. So remember, basically the major thing I have to go on right now is lipids do not have a lot of oxygens, right? Carbohydrates do have a lot of oxygens. So if I were to just use that, okay, could I decide whether this was a lipid or not? So let's count the number of oxygens per the size of the compound that I'm looking at. I'm going to erase this top stuff so I can keep score. That is definitely what erasing looks like. All right, so my lipid. Okay, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. I think 18 carbons, assuming I can count at all, or at least I have to be in the ballpark of 18 carbons. Okay, now I want to know how many oxygens do I have. Five oxygens. Let's compare that to something from our carb page. Pardon the flipping. Okay, so let's pull one of these. So I have 1 carbon, 2, 3, 4, 5, 6. So I'm choosing fructose here. And I have 1, 2, 3, 4, 5, 6 oxygen. All right, I'm going to give me something that we can actually see what I'm doing on. Okay, so I've compared fructose versus cortisol. So what I see here is that for my carbs, I have approximately an equal number. Okay, it won't always be perfectly like that, that's chance. Okay, but I have a pretty equal number of carbons to oxygens, right? So this tells me what we already knew, right? That carbohydrates have a lot of oxygens. Okay, compared to my lipid, we have some. You're never going to have 0 oxygens, right? But compared to how many carbons that I have, okay, it's quite small. Right, that's what, a quarter, a third of the number or something, Matthew? So less than a third. Okay, we got there. Okay, so this is a smaller proportion. And here I chose, or at a glance, I chose the one that I thought had the most oxygens. So if I look at this and I say, well, that is a very small amount of oxygens compared to the number of carbons I just counted, okay, I know this is going to be a lipid, right? Because I have huge sections. And look, I have huge sections of this ring. There's not even any oxygens at all. Okay, and if you flip back and look at your fructose or sucrose or any of our carbs, that never happened. There was always sections that had oxygen. Everybody see those differences? That's very helpful. Okay, so look for those oxygens, right? We want to see a lot more equality between carbons and oxygens and good dispersal, right? It should be pretty even. All right, so this is very uneven. Okay, so these are steroids, right? Steroids are hormones in our body. We likely recognize several of these, right? Male hormones, female hormones that are passed around the body. So these are messengers, right? They might go from the brain very long distances throughout the body. So why is it beneficial that I'm using something like a lipid to send a message and not a carb? Why would I not send a carbohydrate from the brain, say, down to my stomach to send a message? Why would that not be effective? What are your messengers in your body carried in? How does stuff move around your body? In your blood, right? Perfect, right? So if I were to dump a bunch of carbohydrates in your blood, what would happen? They're going to dissolve. Perfect, right? So that's problematic, right? If all of those carbohydrates, these really important messages, were to dissolve the second you sent them out, man, they ain't doing their job, right? So lipids, on the other hand, are the perfect messengers, right? Because we just said they don't play very well with liquids like blood, okay? So we can dump something in there as a lipid. It's going to hang out for a while, right? It's going to be able to sit in your blood, circle, right, and tell whatever cells that it needs to tell without dissolving instantly. Okay, this actually will finish lipids. We will start class with our in-class activity, right, that study guide, so make sure you haven't lost that. Come to class with that on Monday. Go ahead and make that the teacher's question. That doesn't even look like English.